Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome. We're diving into something pretty big today, a kind of crisis almost in modern astronomy. Though maybe crisis of success is a better way to put it.
Yeah, that's a good way to frame it. Our telescopes are just getting incredibly good.
So good that the night sky isn't this, peaceful backdrop anymore. It's more like a nonstop digital alarm, alerts firing constantly.
Millions of them every single night, telling astronomers, hey, look here, something changed.
And somewhere in that constant, overwhelming flood of data, that's where the really amazing stuff is hiding. Exploding stars, black holes ripping things apart. Maybe something totally new we haven't even imagined.
Exactly. These incredibly rare, bright signals. But they're buried, just lost in an ocean of noise.
So today we're looking at a really revolutionary approach, not just to filter out the noise, but to actually, partner with the system generating it.
That's right. We're looking at work from a collaboration University of Oxford, Google Cloud, Radboud University. And they found, essentially a shortcut.
A shortcut to dealing with this data tsunami using AI. And the core finding is, honestly, it's pretty surprising, even for AI development, which moves so fast.
It really is. They took a general-purpose large language model, Gemini 1, not specifically built for astronomy at all.
Right, a generalist.
And with minimal training, incredibly minimal, turned it into an expert astronomical classifier.
And the accuracy was what, around 93%? Which is good, obviously.
Very good, yeah. But that's not even the main story, I'd say. The real game changer, transparency.
Okay. So not just what it decided, but why.
Precisely. Traditional AI, especially in science, often works like a black box. You get an answer, maybe a confidence score, but no clue how it got there.
Which is a huge problem for scientists, right? You can't just blindly trust an output for, say, a once-in-a-lifetime event.
Exactly. But this LLM, it provided a clear, plain English explanation for every single decision. It basically said, here's my conclusion and here's why I think that, based on the images.
That fundamentally tackles that black box problem. It moves us from just using a tool to actually collaborating with something that explains its reasoning.
Yeah, it's a shift from a specialized, opaque program to a generalist intelligence that we can actually talk to and understand.
Okay, let's really unpack the scale of this data problem first, because you need to grasp just how massive it is to see why this AI approach wasn't just nice to have, it was becoming essential. So, paint the picture for us. What's the day-to-day or night-to-night reality for an astronomer dealing with these transient surveys?
Well, you have these incredible telescope networks now. Things like the Zwicky Transient Facility, ATLES, and Mirror Lake T. They're designed specifically for this. They stare at huge patches of the sky over and over.
Looking for anything that changes, right?
Flares up, dims, moves.
Exactly, anything transient. And every time they take a new image and compare it to an older one of the same spot, if there's a difference, bang, an alert gets generated.
And we said millions of these.
Yeah.
Yeah, easily. We're talking hundreds of thousands to sometimes over 1 million alerts every single night.
That's mind-boggling. So if you're the astronomer on duty, what do you even do?
You panic. No, you face this immediate huge problem. Even if you could somehow look at one alert every 5 seconds, 24/7, you wouldn't even make a dent.
You couldn't possibly verify them all manually.
Not even close. So you're forced into this instant triage. You have to rely on automated systems just to filter the incoming stream down to something manageable.
And what are they hoping to find in all that? What are those really valuable signals hidden in the noise?
The cosmic treasures. We're talking about things like supernovae, exploding stars, especially type A supernovae. They're like standard candles, crucial for measuring the expansion of the universe.
Okay, so fundamental cosmology relies on finding these.
Absolutely. Then there are tidal disruption events, TDEs. That's when a star gets too close to a supermassive black hole and gets, shredded, spaghettified. It causes a huge flare of light.
Sounds spectacular, and probably quite rare.
Very rare, and very important for understanding black hole physics. We're also looking for fast-moving objects like asteroids, especially near-Earth asteroids for obvious reasons.
Right, planetary defense.
And then brief, energetic stuff, stellar flares, maybe the afterglows of gamma-ray bursts. Things that need immediate follow-up, sometimes within minutes, before they fade completely.
So high stakes, time critical science, that's the gold. What about the junk? What makes up most of those million alerts?
Oh, the noise. It's vast and incredibly varied. A huge chunk is just stuff that's not astrophysics at all. Satellite trails are a massive problem now, especially with all the new constellations going up.
We just streak across the image.
Yeah, during the exposure. Looks like a transient source appeared and moved.
Yeah.
Very annoying. Then you get instrumental artifacts. Weird reflections inside the telescope, electronic glitches, dead pixels on the camera.
Stuff freaking, basically.
Or just behaving imperfectly. And cosmic rays. High-energy particles zipping through space hit the detector chip and create a little flash. Looks exactly like a faint star popping into existence for a second.
So without a really good filter, you're mostly looking at satellite photobombs and camera glitches.
Pretty much. It's like trying to find a diamond ring in a city landfill at night with a flickering flashlight. The sheer volume of bogus signals is overwhelming.
And this already difficult situation is about to get exponentially worse. You mentioned the Rubin Observatory.
Rubin, yeah. That's the big one coming online soon. It's going to survey the entire southern sky every few nights deeper than ever before. The data volume is just staggering.
How much are we talking?
The estimate is around 20 terabytes of data every single night.
Terabytes. Okay, that's not just a fire hose. That's like trying to drink from Niagara Falls.
Exactly. Forget manual verification. It's impossible. It fundamentally changes the job. Without incredibly sophisticated, trustworthy automation, astronomers become data janitors, not discoverers.
Which is where the traditional machine learning models came in, right, to try and handle this. But they had that black box problem we mentioned.
They did. And they are good at filtering, don't get me wrong. Specialized models, usually convolutional neural networks, can be trained to recognize patterns. This looks like a supernova. This looks like a satellite trail.
But the why is missing.
Completely. The model learns all these internal parameters, weights, and biases to make the decision. But how it uses them, it's opaque. It spits out real transient, 98% confidence.
And as a scientist, you just have to take its word for it.
Pretty much. Or spend precious telescope time verifying things that might be bogus. Or worse, ignore something real. Because the model made a mistake, you can't diagnose. You can't build robust science on blind trust.
Especially when hunting for unique, maybe paradigm-shifting events. You need to know why the system thinks something is interesting.
That's the core dilemma. The volume demands automation, but the science demands transparency. You're stuck between a rock and a hard place.
Okay, so this Oxford Google Radboud team set out to break that deadlock. Their goal wasn't just accuracy, it was accuracy plus explanation.
Exactly. The big question was, could a general-purpose AI, one designed to understand both text and images, not only match the specialists in classification, but also explain itself in a way scientists could trust and use?
And the key was this few-shot learning approach, the minimal input part. You said just 15 examples.
Just 15. For each of the 3 different surveys, they tested Attilas, Mirlicht, and Pan-STARRS. 15 examples of real transients, 15 of bogus artifacts.
Okay, I have to stop you there because that sounds almost unbelievable. 15. We usually hear about training AI on millions of images, needing massive data sets and weeks of computation. How can 15 examples possibly be enough for such a complex visual task, especially across different telescopes with different characteristics?
That's the crucial point, and it really highlights the power of these large pre-trained foundation models like Gemini. Dr. Fiorenzo Stoppa, one of the researchers, pointed this out. It wasn't just the 15 image examples.
Okay, there was more to it.
It was the combination of those few examples plus clear, simple text instructions. Think about it. A standard neural network starts from scratch. You have to teach it everything about shapes, light, noise, context.
Right, it's a blank slate.
But a large language model like Gemini has already been trained on, vast amounts of text and images from the internet. It already has a general understanding of the world, of patterns, of relationships, even of basic physics concepts implicitly.
So it's not starting from zero. It already has a foundation.
Exactly. You're not teaching it what is a dot of light. You're basically saying, hey, you incredibly smart, generally knowledgeable AI, in this specific context of astronomical images, this kind of pattern is what we call real, and this kind of streak or blob is bogus. Here are 15 examples of each to get you started.
So you're leveraging its existing knowledge and just giving it specific rules for this game.
Precisely. Those simple instructions and a handful of examples provide the specialized context it needs. It bypasses potentially years of training required for a specialized model built from the ground up.
That's a powerful concept. leveraging general intelligence for specific tasks. Let's talk about the kind of data it looked at. It wasn't just one picture per alert, was it? It was a set of 3.
Correct. A triplet of images, all linked. This is pretty standard in transient surveys, and it's key to isolating the change for every potential event the LLM got.
Okay, what's the first one?
First, the new image. That's the latest picture taken of that patch of sky. If something new appeared, it's in this image, along with all the background stars, galaxies, noise, everything.
Standard observation.
Yep. Second, the reference image. This is usually a much deeper image, maybe stacked from many previous observations of the exact same spot. It shows what's supposed to be there permanently, the unchanging background.
Like a baseline map of that area.
Exactly. And then the third, and arguably the most important one.
The difference image.
That's the one. They literally subtract the reference image from the new image, pixel by pixel. If nothing changed, the result is just black. Noise, basically.
All the constant stars and galaxies cancel out.
Right. But if a new star appeared, it shows up as a bright spot positive signal. If something that was there disappeared or dimmed, it shows up as a dark spot negative signal, though usually we look for the positive ones.
So this difference image highlights only the change. It's like a cosmic spot the difference puzzle result, isolating the transient event itself.
That's a perfect analogy. It removes all the clutter and focuses the AI's attention squarely on the potential discovery, the thing that wasn't there before.
Okay, so it gets this triplet. But you mentioned it worked across different surveys, Pan-STARRS, Mirror-Licht, Atlas. And the source material notes these have different pixel scales, even though the image stamps were the same size.
Yes, and this is really important for understanding the AI's flexibility. All the image cutouts given to the AI were 100 by 100 pixels. But how much sky those 100 pixels represented was different for each telescope.
Meaning the same object would look different.
Potentially very different. Pan-STARRS has high resolution, about 0.25 arcseconds per pixel. A tiny point source, like a distant supernova, might look like a sharp little dot spread over, say, 5 or 6 pixels.
I like crisp.
But then you look at ATLAS, which has much wider field of view, lower resolution, about 1.86 arcseconds per pixel. That same supernova might appear as just a slightly fuzzy blob contained within maybe 1 or 2 pixels.
So much less detail, almost smeared out.
Exactly. And Mirror-Lake HT is somewhere in between. The LLM, using just those 15 examples per survey and the text prompts, had to learn that the sharp 5-pixel dot in Pan-STARRS data and the faint 1-pixel blob in ATLAS data could actually be the same type of astrophysical event.
Wow, so it had to generalize across different instrument signatures, different noise properties, different resolutions, based on minimal input.
It had to understand the underlying concept of a point source or a streak, regardless of how it was visually rendered by the specific telescope. That's way beyond simple pattern matching.
Yeah.
It suggests a deeper, more conceptual understanding.
Which is exactly what you need to move beyond the brittle nature of older, specialized models. Okay, this brings us to the outputs, the transparency piece. This is where it gets really interesting, moving beyond just real or bogus. What exactly did the LLM provide for each alert it analyzed? There were 3 key things.
Right. This is the package that enables the collaboration.
Right.
First, you get the basic real bogus classification.
Right.
Is it astrophysical or is it an artifact? The fundamental filter.
Standard stuff needed that.
Needed that. Second, the breakthrough. The concise text explanation. A short paragraph describing why it made that classification, pointing out the key features in the triplet of images.
The justification.
It's justification. This is where the black box opens up. And third, an interest score. Basically, a rating, say, 1 to 10, indicating how interesting or unusual this real event might be. Should astronomers drop everything? Or is it likely just another common type of variable star?
So prioritization built right in. That text explanation, though, that seems like the core innovation for building trust. Can you give an example? Like, what would it actually say for a potential supernova?
Sure. Instead of just real 95%, it might output something like classification, real, interest score, a 10. Explanation. Signal is clearly visible as a distinct point source in the difference image, indicating a new object. Morphology is stellar, not streaked like a satellite. Object is offset from the galaxy core in the reference image. No obvious artifacts like diffraction spikes or cosmic rays nearby. Brightness increase is consistent with expectations for a young supernova.
Okay, that's completely different. It's reasoning like an astronomer would. It's ticking off the checklist. Point source, check. Not a satellite, check. Not an artifact, check. Looks like a supernova. Check.
Exactly. It's articulating its thought process using the language and logic of the field. And this wasn't just a theoretical benefit.
They tested this.
They did. They had a panel of 12 actual astronomers, experts in transient science, review a bunch of these AI-generated explanations.
Verdict.
The consensus was that the explanations were highly coherent and useful, meaning they made sense scientifically, and they provided actionable information that the astronomers could actually use to evaluate the alert.
Okay, that's strong validation from the human experts. But then there's this other layer. The AI evaluating itself. It assigned its own coherent score to its explanations. How does that work? Isn't that a bit circular, like asking the suspect to judge the quality of their own alibi?
That's a fair question. It sounds a bit like that, but the coherence score is different from a simple confidence score on the classification itself. It's not rating if it's right. It's rating the quality and consistency of its own explanation.
How so?
It's assessing. Did I manage to construct a logical step-by-step argument connecting the visual features I saw to the final classification? Or was my reasoning a bit messy? Did I contradict myself? Did I have to ignore some awkward feature? If the AI detects features that pull it in different directions, or if the evidence isn't clean, it struggles to write a smooth, coherent explanation.
And that struggle is reflected in a lower coherence score.
Exactly. And here's the crucial finding. The team discovered a strong correlation. Explanations with low coherence scores were much, much more likely to belong to incorrect classifications.
I see. So the AI is basically flagging its own uncertainty, not by saying, I'm only 60% sure, but by saying, my reasoning for this conclusion feels a bit weak or convoluted.
Precisely. It's signaling its own internal cognitive friction. It's like it's saying, look, I'm calling this real, but honestly, the explanation I came up with isn't entirely convincing even to me. Maybe you should double-check this one.
That's incredibly useful. It moves away from silent failures. The system itself helps you identify where the potential problems are.
It's the foundation for a truly reliable human-in-the-loop system. Astronomers are still overwhelmed. They can't check everything. But now, the AI doesn't just give them the most likely real events. It gives them the most likely real. And I classified this, but I'm not entirely sure my reasoning holds up events.
But so it directs human attention to the most scientifically valuable and the most potentially problematic cases. Smart.
Extremely smart. And it had an immediate practical benefit. The team used this feedback. They looked at the low coherence failures, understood why the AI was getting confused, and used that insight to slightly tweak or refine the initial 15 examples and prompts.
A quick iteration based on the AI's own self-doubt.
Yeah. And just doing that boosted the performance on one of the data sets from that initial 93.4% accuracy up to about 96.7%.
Wow, a significant jump, not by throwing massive new data sets at it, but by listening to its uncertainty and giving it slightly better guidance.
Exactly. Smart, targeted refinement enabled by transparency.
Okay, so better accuracy through this feedback loop is one clear win, but the implications feel much broader. You mentioned democratization earlier. How does this approach change who can participate in this kind of science?
That was a major point made by Tron Bulmus, one of the co-lead authors. Because the method relies on such a small number of examples, just 15, and plain language instructions, you suddenly don't need to be a deep learning expert or have access to huge computational resources to use it effectively.
The barrier to entry drops significantly.
Massively. Imagine you're an astronomer who discovers a new, weird type of variable star. With the old methods, you'd maybe need years collaborating with AI engineers, gathering thousands of examples, training a specialized model.
A huge undertaking.
Yeah. But with this approach, you find 15 good examples of your new weird star, write a clear description of what makes it unique, and you can potentially deploy this general-purpose LLM to start searching through survey data for more candidates almost immediately.
So it empowers individual researchers or smaller teams who have deep astronomical expertise, but maybe not deep AI expertise.
Precisely. It shifts the bottleneck from AI programming skill back to scientific insight and curation ability. If you understand the science and can provide good examples, you can leverage this powerful tool.
And this wasn't just the view of the researchers involved, right? Established figures in the field also saw the potential.
Oh, absolutely. Professor Stephen Smart, who's a big name in transient astronomy, been working on this exact classification problem for over a decade, building those complex specialized neural nets.
Okay. So someone deeply invested in the old way.
Very much so. He described the LLM's accuracy, achieved with just those 15 examples, as remarkable. And he explicitly called this approach a potential total game changer.
That's a powerful endorsement. When someone who spent years mastering the complex route sees a shortcut work this well.
It tells you something fundamental is shifting. The era of needing highly specialized, custom-built AI for every single scientific imaging task might be evolving. Generalist models, with the right guidance, are proving incredibly capable.
Okay, so if this transparent classification is the foundation, what's the next step? The paper talks about building agentic assistance. What does that look like?
That's the really exciting future vision. It's moving beyond just labeling images to creating autonomous systems that actively participate in the scientific process.
So the AI does more than just classify.
Much more. Imagine an AI agent. It gets the image triplet, classifies it, real, generates the explanation, looks like a TDE flare, checks its own coherence, high confidence in this reasoning, but it doesn't stop there.
What else does it do?
It starts integrating other data. It pulls the light curve for that object, how its brightness has changed over time. Maybe it checks archives for previous detections, or looks for corresponding signals in X-ray or radio surveys for that same point in the sky.
Building a multi-messenger, multi-wavelength picture automatically, like a human researcher would.
Exactly. Mimicking the holistic approach. And then, if the event still looks highly promising, real, interesting, high coherence, maybe matching patterns in the light curve.
It takes action.
It takes action, autonomously. It identifies the best placed robotic follow-up telescope, one that can see that part of the sky right now. It formats an observation request, need a spectrum of this target at these coordinates, exposure time X, and sends it directly to the telescope's control system.
Without human intervention.
Without immediate human intervention for that step. The robotic telescope pivots, takes the spectrum, and sends the data back.
So within minutes of the initial alert, you could have confirmation data, like a spectrum telling you the chemical composition and distance, all orchestrated by the AI agent before an astronomer even sees the first alert.
That's the vision. For time-critical events that might fade in hours, this automated rapid response could be the difference between catching something amazing and missing it entirely.
That dramatically compresses the discovery timeline.
Hugely. And the key is, the agent only escalates the truly exceptional stuff to the human scientists, the stuff that's genuinely novel or requires complex interpretation.
So astronomers are freed from the filtering and the routine follow-up requests, letting them focus purely on the cutting-edge discoveries the agents surface.
That's the goal. Turn the data tsunami from a burden into a resource managed by tireless, transparent AI partners, freeing up human brainpower for the really hard questions.
And the final piece you mentioned is scalability, because it's low-resource, plain language. This isn't just for astronomy.
Absolutely not. That's perhaps the most powerful aspect. Any scientific field drowning in image data or sensor readings that need classification, particle physics, collision tracks, medical imaging scans, ecological monitoring footage, could potentially adapt this method rapidly.
Just need 15 good examples and a clear description.
Fundamentally, yes. New instruments, new surveys, new research questions. You don't need to start a multi-year AI project from scratch each time. This approach lets the science lead, and the AI adapts quickly. It really could accelerate discovery across the board.
Okay, so wrapping this deep dive up, the core message seems clear. Astronomy was hitting a wall with data volume. The solution wasn't just more powerful, but ultimately still opaque algorithms.
Right. The breakthrough wasn't just brute force filtering. It was building a system you could actually collaborate with.
By using a general-purpose AI, giving it minimal expert guidance, and crucially, requiring it to explain its reasoning. That transparency is what builds the trust needed for real science.
And allows for that self-correction loop, making the whole system more robust. It lets humans manage this incredible data flow without sacrificing the scientific rigor. You can finally trust the machine because it shows its work.
And it's fascinating that the key wasn't massive training data, but rather that small, curated set of examples combined with clear instructions, leveraging the AI's general knowledge.
That minimal input yielding such expert results. It's a really profound demonstration of where these foundation models are taking us. They can become powerful accelerators in highly specialized fields with relatively little domain-specific training.
Which leads us to that final thought, that provocative question for you, the listener, to ponder.
Yeah, if these AI agents can autonomously find an event, explain its significance in clear terms, check their own work, and even task robotic telescopes to gather more data, what does that free us up to do?
What are the next great questions that human scientists, liberated from the immense task of sifting and validating, will finally have the time, the focus, the sheer cognitive bandwidth to tackle?
When your partner handles the urgent, What deep fundamental mysteries do you turn your attention to? Something to think about.
Definitely something to think about. Thank you for joining us for this exploration today.